Alright, so the most recent video I made was about the atomic packing factor, and it was supposed to cover simple cubic, face-centered cubic, body-centered cubic, and hexagonal close packed. However, I did pause it before I started hexagonal close packed, and I forgot to click resume. So I have all my notes right here, and we're just going to talk through them for the last part of that video. So let's begin. So first, hexagonal close packed is going to look a lot like this. Two hexagons with a trio of atoms right down there in the bottom. These atoms fully bisect the equilateral triangles here, here, and there. Well, they bisect on kind of more over here. But that's besides the point. They're exactly halfway up, and they're exactly inside of one of the equilateral triangles, and we'll get into that a bit later. However, we're looking for the smallest repeatable unit. That does not mean they have to be in the same orientation, they just have to be repeatable. So if we have a hexagon, like this, right, hexagon, we can divide the hexagon into 3 equally sized pieces. Thus, the repeating unit is this right here. So our main goal now is to find the volume of the atoms. Then we will continue on to find the volume of the cell. So if we look at the hexagon, right, we can see that this angle A, we're calling it angle A, is going to be exactly twice as much as angle B. And you can do that proof yourself. It's just we're bisecting it with this line. So that means it's exactly 1/2 the full angle, which A is the full angle. So we know that angle A is twice as much as angle B, which is this relationship right here. And so we know that that means angle A is going to have exactly twice as many atoms as angle B is going to have. So since all these hexagons are repeating, if we look at angle A, we see that it's separated into equal thirds of a circle, but we've also cut that top plane off, so that means in angle A, each atom is 1/6 of an atom. And since A has twice as many atoms as angle B does, that means we're going to have 12th atoms in B. So if we look over here, we have 1, 2, 3, 4 angle A's and 4 angle B's. So that means we're going to have 4 1/6 atoms and 4 1/12 atoms. Also, if we look at the line where we bisect our hexagon into 3 equal parts, we see we're cutting an atom in half, so that means we're going to have 2 half atoms as well. So 4 6s plus 4 12ths plus 2 halves is going to equal a total of 2 atoms in the cell. That means the volume is going to be 2 times that 4/3 pi r cubed for an 8/3 pi r cubed, being the volume of the atoms in this cell. So now we need to find the volume of the cell in order to calculate our atomic packing factor. So if we come here and we redrew the cell and we call this top part A, we're not going to have A cubed because it's no longer a cube. We're just going to have to do it as the volume of the cell equals area of the base times the height of the cell. Right, so with the nomenclature that I did earlier, we have area for area and height is Z, and that's going to give us a volume of the cell. So first up, we're going to find the area of the base. If you look up here, if this is the base we have right here, we can see that it is able to be separated into 2 equilateral triangles. So that means it's going to be area of a triangle times 2, which is where we get this 1/2 base times height. Now, if we're using the nomenclature of calling this length A, then that means our base is going to be A. And so our area of that parallelogram on top is going to be equal to the base times the height. Now, how do we find the height? Well, if we have our equilateral triangle and we have all sides A, and A, and we split it exactly down the center like so, we have a 90-degree angle, so we can use our trick. And we're going to call this height H, right? And since it's a 60-degree angle because it's equilateral, we split it exactly halfway down, it's going to be 30 degrees. So the cosine, which is adjacent over the hypotenuse, or h over a, cosine 30 is going to equal h over a, which is also equal to square root of 3 over 2 from your trig table. So you do your algebra to solve for that. You're going to have h equals the square root of 3a over 2. So that means our area, which is going to be base times height, right, is going to be square root of 3 over 2a times a, because a is our base. Now, if we look over here, these atoms are actually going to touch each other, so we can say that a is going to be equal to 2r, which is where, so we get 2r, we square it, so we're going to have the square root of 3 over 2 times 4r squared. 2 and 4 turn into 2, which is where we get this 2 root 3r squared. And that is how we get the area of the base. Now we need to get the height. Where did I put my height? Oh boy. I must have accidentally deleted it. Or I just talked about it right here. Okay, so we'll talk about it right here. So this right here is a bisector. So it exactly bisects the center of this equilateral triangle, and it is exactly halfway up the atom. So we have our z and we have our 1/2 z. There, because z is the total height, and this 1/2 z is going to be exactly what we need. So we have this distance right here. We have this 1/2 z on this edge. I'm going to change colors. This right here. This height from the center of the equilateral to that atom is 1/2 z. And there's going to be this distance down here that we would need as well in order to do another right triangle. So first up, what we're going to do is we're going to find this length in green. So if we have this exactly to the center of the triangle, right, this length in green, and we bisect out to here, we have our right triangle, and we're going to call this distance down here, this red one, we're going to call it C. Some distance C, and that's what's depicted right here. And if we're splitting it exactly in the middle, then we're going to have a 30 degrees, and since we're splitting this length in the middle, it's 1/2 of a, because it's an equilateral triangle. So the cosine of 30 equals the square root of 3 over 2, and that's going to equal 1/2 a over c, or a over 2c. We solve for c, you're going to get a over the square root of 3, right, because that's just the algebra here. So we're going to have square root of 3 over 2 equals 1/2 a over c. Multiply c, divide by 3/2, so c is going to equal a over 2 times 2 over the square root of 3. I'm sure you guys know how to multiply or divide fractions. 2's cancel out, and we're left with a over 3. Now, fortunately for us, in this triangle, this atom right here and this atom right here are touching each other, so that is also going to be 2r. And we've already established that that a we're looking at is 2r as well. So a is going to be equal to 2r, so that means c is going to be 2r over 3. So now we have that triangle, or I'll go back here. This triangle right here, the one that we have written out like this, for 1/2 z. Down here we're going to have what we just solved, 2r over 3. Did I write that down right? Yeah. And this one up here is going to be 2r. We good with that? Or we can just call it a and a over 3. It's the same thing. The math is actually simpler if you use a and then plug everything in. But that's the triangle that we're solving right here. Right, because we did determine what C was, and that was this length right here, or down here at the bottom of this triangle. I'll make it blue so it can be seen a little better. Oop, gotta cover up all the red. Okay. So I know this would have gone better if I'd been writing it, but I didn't want to write it again. Just pause the video, look at the pictures. If you have any questions, post them in the comments, and I'll get back to you as soon as I can. So we do our trig here. We get that a squared, 2r. A squared is going to equal a squared over 3. This turns into a squared over 3. And that's going to equal z squared over 4. You solve for a. 2/3 a squared equals z squared over 4. Then you solve for z. So you're going to get, or you combine your a's and then solve for z. You're going to get 8 over the square root of 3. So it turns into this. Solve for z. I'm sure you can do trig by now. Hopefully these triangle diagrams are helpful for you. Then finally we come over here. The volume of the cell is going to be equal to the area times z. The area we solved as 2 square root of 3 r squared. And z we solved to be 4 square roots of 2 over the root of 3r. Multiply those together, you're going to get 8 root 2 over r cubed. We've already established that the volume of the atoms is going to be 8/3 pi r cubed. So that goes on the top, and then that 8 root 2 r cubed turns into pi over the square root of 3 root 2, which turns into 0.74. So that means 74% of the atoms, or 70% of the volume of the cell, is occupied by atoms. You will notice that this is the exact same packing factor as face-centered cubic. If you look into that, it's actually pretty interesting. I'm not going to spoil that for you. Now, the last thing we're going to talk about is ionic. I'll use my pen. The last thing we're going to talk about is ionic packing factor. I'll go back to print because I know my handwriting's not the easiest to read. Ionic packing factor. And the only difference is with an ion, you're going to have 2 different atoms. So let's say we have some CAF. No, let's not do CAF. Let's do potassium iodide, Ki. And I'm just making this up, so it could be anything, but let's say we're going to have our face-centered cubic for Ki, or body-centered cubic for Ki. So if we draw our cell, we're going to have the corners be iodine, and the face is going to be potassium. Or it could be something different. So when you're trying to determine the ionic packing factor, instead of instead of that distance right there being 4r, whatever it's going to be r iodine, r potassium, or yeah, r potassium, 2r potassium plus r iodine. And so the only difference is you're going to plug in different r values.